So starting with pH today, I've added these in. So you, of course, remember from Chem 1, hopefully, that in order to get the pH of a strong acid or a strong base, you're going to take the negative log of the hydrogen concentration will give you pH. And then the negative log of the hydroxide will give you POH. Together, pH and POH equals 14. Which if yesterday we talked about the KW value being 1 times 10 to the negative 14, guess what happens if you take the log of 1 times 10 to the negative 14? What do you get? 14. Okay, so that's where the 14 comes from. If you are given the pH of a strong acid or the pH of the strong base, you can then determine the hydroxide concentration or the hydrogen concentration based on taking the antilog. Okay, so you would take whatever your pH, so let's say you had a pH of 4, you could say 10 to the negative 4, and that would be your hydrogen concentration. Okay, if you're trying to find hydroxide, subtract the pH from 14 first. Okay, anytime you're dealing with bases, you got to do that little extra step of, if I take the negative log of my concentration of my base, that's giving me POH. So in order to get to pH, I'm going to have to subtract from 14. So just don't forget that extra little step, because it's done the same way, it's just that when you're hydroxide, you got to get it over to pH. Okay? Here's a scale kind of showing you some things that, everyday things that you're used to in your looking around your world, and that's some of their pHs. Vinegar, which is acetic acid, very dilute, is a pH of 3. Your stomach acid would be a pH of 2. 1 molar HCl is a 0. Okay? It's just, yeah, we don't really do negative pH, that's just as acidic as you can get. Okay? So if you have a higher molarity, it's going to even, just be decimals. Okay? But generally we go 0 to 14, and then 1 molar NaOH is going to be 14. And then your blood is slightly basic. Pure water is 7. Something else that's 7 is alcohols. They are neutral pH as well. Okay? So here is something, I don't know if you remember this from Chem 1, but when we are doing significant figures for pH, we are going to look at the decimal places. So if I have a pH of, say, 4.87, I look here and say my concentration needs to have 2 significant figures. It's probably Cameron, yeah, and he's got crutches. So.
I thought there was there was stuff with negative pH, and there was stuff with like a 15 pH.
We usually just go 0 to 14. Okay? There are some things that will come out that calculator-wise, but our scale is 0 to 14. Okay? But this is how you do sig figs for pH, is you look at your decimal places, and that's how many sig figs should be in your concentration. Okay? All right, so we can only do the pH and POH for strong acids and strong bases. Okay? That's the only time you can use that negative log right off the bat. Okay? We're going to do weak acids and bases in here in a little bit. So this is pretty straightforward. Remember, we have the, that just keeps disappearing, doesn't it? Remember, KW is equal to the hydrogen concentration. Why is this thing doing this? It's, yeah. I'm not sure what's going on. I really don't know what's happening. Okay? It's not showing up on here, so the recording, it's perfectly fine, but for your screen, I don't know. I don't really know. So, all right, so this one is giving us a concentration of hydroxide. So it wants us to calculate the hydrogen. So if we want to calculate the hydrogen concentration, we can do 1 times 10 to the negative 14. Okay, hopefully our technical difficulties are over. Okay, so in this case, in order to get the hydroxide concentration, you're going to do that 1 times 10 to the negative 14, which is your KW value, divided by 10. And so then this is going to be 1 times 10 to the negative 15 molar for your hydroxide. So we'll go back and say this first thing, your hydrogen concentration is times 10 to the negative 9, which is less then times 10 to the negative 7, so this is a basic solution. Okay, and then of course, if you're negative 7, this is neutral. And then what would this last one be? Well, you got 10 molar hydrogen concentration, so that is definitely acidic. Okay?
It's like super.
Yeah, it's super acidic. Okay. All right. All right, so that is how you do concentrations. When you know one, you can find the other one because you know that KW value. So let's look at this next slide.
So Miss Parker,
I did it again.
wait, Miss Parker,
Yeah?
for that last one, what would the pH be for it? Is it like a 1.0 times 10?
You would do negative log of 10. See what it's going to come out to. It might come out to a negative number.
Yeah. I think it would.
Comes out to a negative 1.
How is that possible for pH? I guess it's just one of the.
I mean, it's because it's so concentrated. Yeah. I think I've lost my internet connection here. It's trying to. All right, so the next one is exercise. We did 6, right?
Yes.
Okay, so we should be on 7. So this says calculating pH and POH. So if I want to calculate the pH and POH right here, for this POH, I'm simply going to take the negative log of the 1 times 10 to the negative 3, and I get that it is 3. So if I want to get pH, I'm going to take 14 minus 3, and I would get a pH of 11, which is definitely basic. And then for the next one, to get that, I would say the negative log of 1.0. So that would give me a pH of 0, actually. So then my POH would be 14, which would definitely be acidic. For sure, for sure. Okay? So hopefully that rings a bell on how to do pH and POH. I think there's one more. Do I need to do the next one, or are y'all good with that?
Let's do it.
That is in no way attached to the
Exercise 8. Okay, so pH sample of human blood was measured to be 7.41. Calculate the pH, calculate the POH, the H plus, and the hydroxide for the sample. So let's start with what they gave us. They gave us a pH of 7.41. So very quickly I can do a POH of 14 minus 7.41 is 6.59. Now in order to get my hydrogen concentration, I can do 10 raised to the negative 7.41, which is antilog. So that would give me 3.89, because I need 2 sig figs because of that, times 10 to the negative 8 molar. And then the hydroxide, I would do 10 raised to the negative 6.59, and that would give me 2.57 times 10 to the negative 7 molar. They didn't put their answer down here in 2 sig figs. Yes, they did. I messed up.
Yeah, you
Oh.
did 3.
I got it. Ah, it was my fault. 3.9. I was thinking decimal places, not sig figs. There we go. Now it's right. My bad. Okay, so straightforward enough. I'm not going to do exercise 9 because you guys can do that. Let's do the exercise 10 though. Does everybody have this before I go on? Okay. That's pretty straightforward for strong acids, but let's just do one for strong bases. We are going to take the negative log, because this is going to give us POH because we're dealing with hydroxide. So So negative log of 5 times 10 to the negative 2, which is going to give us 1.3. So the pH is going to be 14 minus 1.3. Since we have 2 sig figs here, we need 2 decimal places for our pH, so it would be 12.70 is our pH, which we would expect it to be basic. It's got a fairly high concentration of sodium hydroxide. Okay? So we're good with pH of strong acids and strong bases? They're the easy ones. Because guess what is fixing to make, that's very Southern Texan thing to say right there, fixing to make an appearance.
Depression.
Possibly, but I'm talking rice tables.
Ajay was right.
All right, so when we're calculating the pH of weak acid solutions or weak base solutions, it works both ways, we're going to need to use our Ka and Kb values, and we're going to use the rice table. Yay, I know you're so excited. Okay, so here's an example of a weak acid, of acetic acid. Gives us our Ka value. Do your rice table, and this is what it should look like. Sometimes you will be able to neglect X, sometimes you will not, okay? But there's actually a fairly easy way to tell in here of when you can, okay? So here is this. We do all the change and equilibrium and we plug it in. Here is the best way to know right here how you can, if you can neglect X or not. And it has to do with your concentration and compare it to 100 times your Ka value. Okay, so in this case, our Ka value for acetic acid is 1 times 10 to the negative 5. So 100 times that would be this, which is right here. And if we looked at our concentration, it's too close to it. So we could not, it's not within the less than 5%. So we would have to keep X there. So that's a quick way to compare. Anytime you are neglecting X, whether it is in acid-base equilibrium, whether it's in general equilibrium, you must say that you're neglecting X. Okay, you have to say that I'm going to neglect X or whatever, and then when you do, you say within 5% once you do the calculation. So don't just neglect it and forget to check, is it within 5%? Because if it's not within 5%, then you can't neglect it. In most cases, you will be able to, because quite honestly, they're probably not going to put a quadratic equation one on the AP exam because it takes too much time. That doesn't mean that they won't at some point in time. Yes, sir?
So like, once you neglect it or whatever, that goes in, like, eventually you get to Ka value by neglecting it, right? Or do you, or just
Usually when you're neglecting X, you're not, usually you have the Ka value, and you're trying to get what X is.
what the concentration is, right?
And so if your concentration is fairly high and X is really, really small, that's why you can neglect it. Because say if I have a concentration of like 0.025 and my X ends up being like times 10 to the negative 5th, when I subtract that, I'm still going to end up writing down 0.025 because we're only putting so many decimal places out there. Yeah, that's why we can sometimes neglect X. Yes?
Once you multiply Ka times 100 and compare it to the initial concentration, what is like too close?
It's got to be less than 5% difference. So if your concentration is like more than 5%, anywhere, you know, then you have to, it's just a kind of a ballpark. If you don't want to neglect X, no one's going to make you. Like if you just, but in most cases on the AP exam, you're going to be able to for acid base because the quadratic equation just takes too long. But one thing I want to caution everyone on is when I'm grading these AP exams and these AP questions, some of you guys are losing points because you're not showing me how you get your numbers. Okay? Some of you just have this number up here in the problem, and while it may be a right number, you have to show the stoichiometry or show the relationship of how you got that number. You can't just have it appear. Okay? And some of you are losing a lot of points because you're assuming that the reader knows why you did that. You can't make that assumption. You've got to show the work. It may make sense in your head and you go, okay, I'm going to use it, but you have to show them that you know what you're doing, okay? Because you could have just gotten lucky and gotten the right number. You have to show them, and some of you are losing points for that, and that's a silly thing to lose points on because clearly you know how to do it. You just have to prove you know how to do it, okay? So I'm trying to leave you notes like, where'd you get this number? So instead of getting the 2 points for that question, you only got the 1 point because you didn't explain where you got that number. So I want to caution you of that as we get closer and closer to the AP exam. Okay, so let's continue working through this. Here's some proof of why you can't neglect X. You can read through all that. It takes you through the explanation because I want to get to working the problems because you can read on your own. So here is the same, this different, I think it's a different concentration this time. Yeah. We got the pH of a 10.10 molar if we get the Ka of an acetic acid. Again, by cross-multiplying and not neglecting X, you get this number. She's taking you through this process, okay? And then you get a pH of 0.288, okay? And then the second way is if we had neglected X, we would get a pH of 0.287. So that's a good approximation. But this time we had a really, really high concentration, which is not going to be anywhere near our 100 times Ka value. Okay? So, most likely on the AP exam, I've never seen a quadratic equation show up. You never know. They might want to like make liars out of us. So let's work some problems. Here is the steps you want to take. First of all, set up your rice table. Okay? Solve for X the easy way, meaning drop it. Say assume X is negligible, and then use the 5% rule to verify if the approximation is valid. And that means then you can calculate the hydrogen and the pH. So once you get your hydrogen concentration from your rice table, then you can do negative log of that. Okay? But it's never going to be the concentration of your original amount because you got to go through the rice table. Okay? All right, so pH of a weak acid, we have hyperchlorite. Y'all ready? All right, if you're okay with this, because I won't have room, I'm going to make a blank page, but you have room, I think, on yours, but I will not be able to fit it all in that tiny space. Okay, so we have the HOCl. So we're going to do our rice. So we start out with this concentration. And 0 and 0. So this is going to be minus X. This is going to be plus X. And this is going to be plus X. So at equilibrium, we're going to have 0.100 minus X. X and X. They gave us the Ka value, didn't they? Yes, they did. So Ka is going to be equal to H plus OCl minus and HOCl. Right on top of it. Sturdier in your notebook.
Oh, that's fine.
Okay. Okay, so we plug in what we have, and we have 3.5 times 10 to the negative 8 is going to be equal to x squared over 0.100 minus x. So I would say this, neglect x. Then I'm going to say 3.5 times 10 to the negative 8 is equal to x squared over 0.10. So x squared would be 3.5 times 10 to the negative 9. So then I square root it. X is going to be equal to 5.9 times 10 to the negative 5. So that is within the 5% rule. So now this is equal to, and this is what I would say, don't just say X, say X is equal to that which is equal to the hydrogen concentration. So that when you can say this, therefore, negative log of 5.9 times 10 to the negative 5 is equal to a pH of 4. What do I need here? 2.3. Technically, is it, they gave us 0.100, so 4.23. I can't fit my 0. There I go. Okay?
Can you give us a second to like kind of think about that?
Yes, I can. Because now I'm going to walk you through it.
Oh, okay.
Yeah.
How do you know it's within the 5%?
Once I get my value for X, which is 5.9 times 10 to the negative 5th, I compare that to my original concentration.
Oh, I think you said that you could use like the molarity that they give you for the initial.
You can do that as well. My old way is I compared. That number is way less than 5% of it, so I can use it. Yeah.
Isn't it says it's like 0.1 molarity, which is like way bigger than Ka.
Yeah. That you can do that as well. But I mean, you always still show that you're checking within 5%.
But I mean, isn't like if it was bigger, like since it's 0.1 molarity compared to like 3.5 times 10 to the 8, like you couldn't neglect it like off of the concentration or something, or like I'm something that wrong. Right? Because like 0.1 is a lot bigger.
Well, if you take 100 times your Ka, you're at negative 6. 0.1 is a lot greater than negative 6, so you're going to be able to neglect. Are you looking at it backwards?
Oh, okay. So it's if your original
Yeah, if your concentration is close to your 100 times Ka, then you can't. Well, 0.1 is a lot stronger than times 10 to the negative 6.
So like you would take 10 to the 3.5 times 10 to the negative 6 over 0.1 and see.
Well, you don't have to do, I mean, I think you don't even have to even do that. I can look at that and say 0.1 is negative 1, right, times 10 to the negative 1. It is much, much greater than times 10 to the negative 6.
But if your say your molarity was like a lot smaller,
If your molarity was a lot smaller,
like it was the other way around.
don't start with me, you stupid thing up there. Not you. The thing. I'm not talking to my student, I'm talking to the board.
So I thought you were saying,
Where are you getting times 10 to the negative 6?
I'm pretty dumb.
If you took, this was your Ka value right here. Remember it said 100 times your Ka value would make that a times 10 to the negative 6.
Okay,
And you
so-
compare it to this right here, they're way, way different. So you can neglect X. But if I had been like 0.00001, which was really close to my negative 6 value for the Ka, then you couldn't do that.
But what if it was like the opposite way? To
How about Jared? You're confusing people. How about we work a couple of problems and see if that, or we have that conversation privately? Because I see confusion setting in.
Well, I was confused because I thought originally it was like with it being like that the concentration
Yeah.
being 5% of
Yeah.
the actual Ka.
Usually, if you have a what I call a higher concentration of an acid, you're going to be able to neglect X. It's when you have a really small, like 1 times 10 to the negative 4 concentration, then it's going to be an iffy.
So it's always going to be the way where it's like you have the Ka, or sorry, the molarity has to be a lot greater than the Ka.
Yes, your molarity needs to be a lot greater.
So
Okay?
Ka would be 5% of molarity, and then you can go neglect it if it's 5% smaller.
Yeah.
I don't know.
So,
Okay. So do you want me to walk you through this process now that we answered that question? Okay.
Yeah.
can I ask,
So let's walk through. We understand what we did here, hopefully. That's a rice table. That's last unit. You just do your change in equilibrium. Then we plugged in our values here from here, here, and here. Right? We have such a great concentration here compared to our Ka value that we neglected X. Because you don't have to, but then you would have to do a lot more difficult math, like the quadratic equation. And quite frankly, on the AP exam, you want to try to do these as quick and painless as possible. So you should always try to neglect X and then see if it doesn't work.
are there like specific, like,
Can you use like any calculator you want?
Yes, you can use, well, that's actually not true. The only person here that has a calculator that might not be able to be used is a J.
What?
Is yours in there's an approved list on the
Is the 89 on there?
college, huh?
The 89, do you know?
I'll pull up the list and let y'all know before. Oh, this is sidebar. Has everybody registered? Ooh, I need to do my own child for AP exams. It's after, if you wait till after the 19th, they go up by $10.
They're already like $98.
Yeah.
They've gone up a lot over the years. Okay, so after we neglected X, then we just did our math and collected our terms. So I did this times this, and I got X squared was equal to that. Take the square root. So now I look at that, and here's how you can kind of see that you know you can neglect X, because if I was to take 0.100 minus 5.9 times 10 to the negative fifth, what would I still have on HOCl? 0.1. So yeah, that's how you can check that too.
Yeah, mine's allowed.
Okay, yours is allowed. Yeah, there's on the college website, College Board, you can see.
Yeah.
So once we get our hydrogen concentration, then we can take our negative log just like we do for a strong acid, and we get that. We're going to work another one. I'm not just going to work one and send you on your merry way. Okay?
So like at the very end, you're saying we can check it by subtracting the X value from the original molarity.
Mhm.
If it's still like the same number when you round it.
Yeah.
Okay.
Correct.
So that's like a double check.
Yeah, and I would make sure I state within 5%. So or assumption is good. You know, state something so they know that you know to check the assumption. Okay. All right. So. All right. So when you're doing a mixture of weak acids, you're going to only look at the one with the largest Ka value, because it's the only one that would contribute any appreciable or measurable amount of hydrogen. So you're going to determine the pH based on this and ignore any of the others. So this next one is going to be a mixture. I think it's exercise 12. Okay, so you have a mixture that contains 1 molar of HCN, and it gives you a Ka value, and 5 molar of HNO2, and it gives you a Ka value. So you're going to calculate the concentration of the cyanide in the solution. Okay, so but in terms of your pH, it's going to look a little different. Okay, so I'm going to again do a new blank page because I can't fit my work on there. I write too big. Okay, so the one with the larger Ka value by significant amount is the HNO2. So we're going to start with that. So we start with 5 molars, which is a large molarity. 0, 0 minus X plus X plus X. And it does not take that long to throw your rice table on there, so I highly suggest that you do that instead of just putting in there that it's equal to X squared over 5. Show them that you know how to do this, okay? Because sometimes some of the points may not necessarily mean that you wouldn't get the answer right, but sometimes the point is just setting up the rice table. And if you skip that, they don't give you the point for that. All right, so now we have the Ka is equal to H plus NO2 minus over HNO2. So we're going to plug in. Oh, it's not. So what do you think? Can we neglect here?
Yes.
Yes. So then we're going to say
Thank you.
I'm gonna run out of room, so I'm gonna put this over here. 4.0 times 10 to the negative 4 equals X squared over 5. So X is going to be equal to 0.0447. So pH I think is 1.35. So that was the first box. Next one they want to say also calculate the concentration of the cyanide ion in this solution at equilibrium. So I'm going to do that in a different color. Before I go to the cyanide, would anybody like some? No, I'm just kidding. Y'all are funny. Do you understand this process, what we just did?
The part that just confuses me is neglecting X when you choose to do that and when you don't.
If your concentration is really large, you're going to be able to neglect X.
Okay.
Would you consider 5 molar really large?
Yes.
Yes, so neglect X.
So,
Yeah.
is this right?
And to be quite honest with you, on the AP exam, if they're giving you an acid-base equilibrium problem to work like this, you're going to be able to neglect X. Otherwise, the math becomes a little too complicated. I mean, I would say 98% of the time, I would bet 98% of my, I don't know, something. Chocolate.
Your teacher's salary.
I'm not betting my teacher's salary on anything. I got kids to pay for college and weddings to pay for, and I want a new car. After I have to wait for Mackenzie to get out of Rice before I can get a new car. I don't know. Yeah. Okay, so now let's do the cyanide. So for cyanide, the Ka would look like this: H plus, Cn minus, and HCN, right? So it would look like that. They gave us the Ka value, which was 6.2 times 10 to the negative 10. We calculated what the hydrogen value was, because remember, it's the only one offering a appreciable amount. So it's 0.0447. That's supposed to be a bracket. I mean a 7 now, the bracket. We don't know the cyanide concentration, but we do know HCN, which they gave us was 1 molar. So when we dump all that in the calculator, we should get a concentration of 1.4 times 10 to the negative 8 molar. Okay? Does that make sense how I did cyanide? Okay, then we will stop there since the bell rang.